Hey guys, and welcome to another video on vectors. Today we're going to be looking at the scalar projection of a vector. So what I've got on the graph here is I've got a vector A and I've got a vector B. And what we want to do is we want to project vector B onto vector A. So what does that look like? It's kind of like a shadow. So imagine that we have the sun above both of the vectors. We're trying to find out the length of this section here. So we're trying to find out what's the length of the shadow that's being projected onto A. And so if we just move the A across, we're trying to find that length over there. And the words we use for that length, so if you're trying to find the scalar projection of B onto A, we usually call that the component of B on A, and that's how it's represented down here. So it's the component of B on A. And obviously, if we're looking for the length, we'll also talk about the modulus of B being the length of vector B. So in the last lessons, we were looking at the dot product rule. And we're going to use the dot product rule to actually help us find this scalar projection of B onto A. So we know that cos of theta is adjacent, so the component of B on A divided by the hypotenuse, and in this case, in this right angle triangle here, the hypotenuse is the modulus of B. Just by rearranging that quickly, what we'll see is that the component of B on A is the modulus of B times cos of theta. Now, if you look above up here, what you might notice is that the modulus of B cos theta also appears up here. So this part of the equation, modulus of B cos theta, is actually the same as the component of B on A. So that bit there is the same as that bit down there. And that's what we're trying to figure out. We're trying to figure out what this length is. So if that's the component of B on A, what we need to do is we need to move this modulus of A to the left-hand side there. And what that looks like is we'll end up with A dot B over the modulus of A. So if we're trying to find the scalar projection of vector B onto vector A, we can just use this formula over here to help us find the scalar projection of B onto A. And this becomes really useful when we're finding the minimum distance between two lines, or if we're finding the minimum distance from a point to a plane. There's lots of applications of this result over here. Let's look at some examples now. And I've got the little formula that we had on the previous slide up here. And the first example wants us to find the scalar projection of this vector B onto A. Now, we can draw any picture that will represent the situation. I find this to be the easiest picture to draw. So it doesn't matter what the vectors are. This will be our basic picture over here. So we want to find the component of vector B onto vector A, and that's going to be the dot product between A and B divided by the modulus of A. So we need to work out these two things first. So our A dot B is going to equal negative 231.112, and that gives us negative 2 times 1 is negative 2, 3 times 1 is 3, and 1 times 2 is 2. So that's just a value of 3. Next, we need to figure out what the modulus of A is. So the modulus of A is going to be the square root of each of its components squared. So negative 2 squared is 4, 3 squared is 9, and 1 squared is 1, which is root 14. So the scalar projection of B onto A, the scalar projection of B onto A is going to be 3 over root 14. And if you wanted to rationalize that denominator, that would be the same as 3 root 14 all over 14. Let's look at the next question now. If A is 3, 0, negative 1, find a vector B such that the component of B onto A equals 2. So again, we'll use this formula here, and let's just write in what we know. We know that the component of B onto A is 2, so we're going to have 2 equals A dot B divided by the modulus of A. And we can work out what the modulus of A is going to be as well. So we can have the modulus of A is the square root of each of the components squared. So 3 squared is 9. 0 squared is 0, and negative 1 squared is 1, which gives us root 10. To get rid of the divide by modulus of a on the right hand side, we'll times it to the left hand side. So we'll have 2 root 10 equals a dot b. Now we also know that a dot b is going to be vector 3, 0, negative 1 multiplied by some vector b that has a value of x, y, and z. At this point here, we have quite a lot of liberty in how we decide what the vector b needs to be, because it just says find a vector b. It doesn't say find the vector b. So in this case here, I'm going to say let x equal 0, let y equal 0, and you can see what's going to happen there, because when we multiply 3 by 0, we can have 0. 0 times 0 is 0, and we're going to have minus z. And as you can see here, all we need to do is make sure that minus z is going to equal 2 root 10, which means that z is going to equal negative 2 root 10. Now we've got our vector b. Our vector b is going to be 0, 0, minus 2 root 10.